Hello everyone, welcome to Prayogik Unknown channel. In this video, let's learn about operational amplifiers. They are also called in short as op-amps. As the name suggests, these are devices which are used to carry out mathematical operations. For example, you can use op-amps to add, subtract, or to integrate or differentiate, and in the old analog computers, these op-amps were used to make all the mathematical calculations. So how does an op-amp look like? You can see here I have drawn an op-amp. The op-amp needs two power supplies. One is the V plus and the other one is the V minus. And it also has two input terminals. One is the positive terminal, which is also called as non-inverting terminal, and the other is the negative terminal, which is called as an inverting terminal. And it has one output terminal. So let's call the non-inverting input as V in plus, and the inverting inputs, let's call it as V in minus. One of the important characteristic of op-amp is that it provides a very high input impedance at its input terminals and a very low output impedance at its output. What this means is an op-amp doesn't draw any current into its input terminals, and it provides maximum current at its output. This characteristic of the op-amp is very useful when we interface sensors. The high input impedance doesn't draw any current from the sensors, and whatever current that is required for the circuit will be provided by the op-amp. And also please remember that the op-amps have a huge gain in the order of 10 power 6, which means that any small change in the input signal will lead to a huge output change. So let's look at how the output of the op-amp changes with respect to the input. The output of the op-amp V0 can be given by the gain multiplied by V in plus minus of V in minus. So you can see that effectively what the op-amp does is it takes the difference of these two inputs, which is V in plus and V in minus, and multiplies with the gain of the op-amp and provides the output. You can see that op-amp also functions like a differential amplifier. So it's amplifying the difference between the two input terminals. Majority of the times when we are using op-amps in the circuits, usually we use it with a closed loop configuration. We will be dealing with the closed loop configurations in the next videos. For the current video, let's limit the discussion to the open loop. The simplest way to use the op-amp in open loop configuration is to use it as a comparator. For example, let's say we connect ground to the negative terminal and provide an input voltage at the positive terminal. So in this configuration, if the input voltage goes above ground, which is 0 volts, so any voltage above ground will result in the op-amp providing a high output, which is going to saturate at V plus. Please remember that any small change in the input voltage multiplied by a huge amount of gain will result in saturation of the output voltage, which is V plus. And then any input voltage below the ground will result in the output swinging back to V minus. So for example, let's say we provide a sine input at the non-inverting terminal. So effectively what is going to happen is, as soon as the sine wave goes above 0 volts, the output is going to swing to V plus, and when input comes below 0 volts, output is going to swing to V minus. This way we can use this circuit to produce a sine wave to square wave converter. Let's go ahead and build this simple circuit and see the output. Also remember that when you are testing the op-amps in your lab, you can also use these connections to verify whether the op-amp is working or not. So this is a very simple connection. You can just connect the negative terminal to ground. The positive terminal you can give a sine wave as an input and check at the output terminal if you are getting a square wave or not. So this way you can verify if the op-amp is working or not. So these are the two very popular op-amp ICs. One is LM358 and the other is LM324. You can see that LM358 has 2 op-amps in it and LM324 has 4 op-amps. In terms of operation, both the ICs are similar except that LM358 has just 2 op-amps and LM324 has 4 op-amps. So based on which IC you have, make the connections accordingly. So for example, in case of LM358, pin number 8 is VCC, which means V plus, and pin number 4 is V minus. So if you have LM358 with you, you have to provide V plus to pin number 8 and V minus to pin number 4. Similarly, if you have LM324 with you, then you have to provide V plus to pin number 4 and V minus to pin number 11. So these are the differences in the connection. Now if you are using LM358, you can see that the positive input, which is the non-inverting terminal, is at pin number 3 and the inverting terminal input is at pin number 2 and pin number 1 is the output. And that's the similar case in LM324 also. So the positive non-inverting terminal is at pin number 3, inverting terminal is at pin number 2 and the output is at pin number 1. So let's go ahead and make the connections accordingly and see if we can get a square wave when we provide sine wave as an input. Here I am using LM324, so I'll be making the connections as per the LM324 pinout. If you have LM358 with you, kindly refer the pinout of LM358 and make the connections accordingly. I'm connecting V plus to pin number 4 and now I'm connecting V minus to pin number 11. Let's connect the inverting input to ground. So it's pin number 2 in case of LM324. Now in header number 1, you can see that there is an input called sine. So what I'm going to do is I'm going to connect a wire and provide it to the non-inverting terminal, which is pin number 3. Now from the output pin, which is pin number 1, I'm going to take a wire and connect it to the oscilloscope channel AN1. So in header number 4, you can see we have 2 oscilloscope channels, AN1 and AN2. So I'm going to connect the output, which is pin number 1, to AN1. I would also like to measure the input. So what I'm going to do is I'll take one more wire and connect the non-inverting terminal to AN2 of the oscilloscope channel. So let's check if we are able to get the output. Yes, you can see that channel 2 is sine wave, channel 2 is sine wave and channel 1 is square wave. So this way we can come to know that this op-amp is working, and this is a very simple zero crossover detector circuit. So why it's called zero crossover detector circuit is, as soon as the input voltage goes above 0 volts, the output is going to swing to V plus, and as soon as the input voltage goes below 0 volts, output is going to swing to V minus. You can have a look here. When I merge both the channels, you can see that when the voltage goes above 0 volts, the output has swung to V plus, and when the voltage goes below 0 volts, the output goes to V minus. This way you can use this circuit as a sine wave to square wave converter. So this circuit gives a very basic understanding of the op-amp, and even though this is not a very perfect circuit to convert sine wave to square wave, you can still use it as a crude sine wave to square wave converter. This is also a very simple and good circuit to test whether your op-amp is working or not. Please keep in mind that the output voltage swing is limited by the power supply voltage you have provided at V plus and V minus. For example, if you provide 9 volts and minus 9 volts here, so there is no way that the output is going to go above this or below this value. Okay, even though the gain of the amplifier is in the range of 10 power 6, the output swing voltage is limited by the V plus and V minus voltage provided to the op-amp. I hope this gave you a basic understanding of how we can get started with op-amps. So further in future videos, we will be looking at different configurations of the op-amp and we will be dealing with much more complicated circuits. Thank you for watching the video.